In the vast, silent expanse of our solar system, comets are among the most enigmatic travelers, fragile, icy wanderers that originate from the distant reaches of the cosmos. Some are born in the cold depths of the Kuiper Belt or the Oort cloud, while others hail from beyond our star system entirely, arriving as interstellar interlopers. These celestial bodies follow elliptical or hyperbolic paths, drawn inexorably by the gravitational pull of the Sun. As they approach their closest point to the star, a moment known as perihelion, they face a trial of survival. The distance at which a comet reaches perihelion can mean the difference between enduring the Sun's fury and succumbing to its intense heat, disintegrating into a cloud of dust and gas. Two comets currently captured the attention of astronomers and stargazers alike: C2025 R2 SWAN and 3I Atlas. While both are on trajectories that bring them into the inner solar system, their fates are starkly different due to their perihelion distances. C2025 R2 SWAN is hurtling toward the Sun at an incredibly close 0.5 AU, placing it within the innermost reaches of Mercury's orbit. At this distance, the comet will experience extreme solar radiation and tidal forces that could lead to fragmentation or complete disintegration. In contrast, 3I Atlas, an interstellar comet originating from outside our solar system, is following a safer path with a perihelion distance of 1.36 AU, which places it between the orbits of Earth and Mars. This seemingly modest difference in distance holds profound implications for each comet's survival and the insights they offer into the nature of comets themselves. The significance of perihelion distance extends beyond mere astronomical curiosity. For C2025 R2 SWAN, a 0.5 AU perihelion means it is at a much greater risk of disintegration. The intense solar heating can cause rapid sublimation of its icy nucleus, leading to the release of gas and dust at an accelerated rate. If the comet cannot withstand the thermal stress, it may fragment into smaller pieces or even vanish entirely, leaving behind only a trail of debris. On the other hand, 3I Atlas's more distant perihelion ensures a relatively gentler encounter with the Sun, allowing it to maintain its structural integrity and continue its journey through the solar system without succumbing to the same fate. Moreover, since 3I Atlas is on a hyperbolic trajectory and will eventually escape the solar system, it does not pose a direct threat to Earth, unlike some comets with more elliptical orbits that can return periodically. This cosmic race between C2025 R2 SWAN and 3I Atlas highlights the delicate balance between a comet's resilience and the destructive power of the Sun. The closer a comet ventures to the Sun, the more it must contend with extreme conditions that can determine its ultimate destiny. In the following sections, we will explore the science behind these comets' journeys, delve into the factors that influence their survival, and examine the broader implications of their perihelion distances. By understanding the differences between C2025 R2 SWAN and 3I Atlas, we gain a deeper appreciation for the forces that govern the behavior of comets and the lessons they offer about our own place in the universe. To fully grasp the significance of the perihelion distances of C2025 R2 SWAN and 3I Atlas, we must first understand the fundamental principles governing cometary orbits and the role of perihelion in a comet's life cycle. Comets are celestial bodies composed primarily of ice, dust, and rocky material, remnants from the early formation of the solar system. Their orbits are highly elliptical, often stretching across vast distances, and they are influenced by the gravitational forces of massive bodies such as the Sun and planets. The closest point in a comet's orbit to the Sun is known as the perihelion, and this critical juncture determines how a comet interacts with solar radiation, temperature, and tidal forces. C2025 R2 SWAN is hurtling toward the Sun at a perihelion distance of 0.5 AU, placing it within the innermost regions of the solar system, closer than Mercury's orbit. To put this into perspective, 0.5 AU is approximately 75 million kilometers, 46.6 million miles from the Sun, less than half the distance between Earth and the Sun. At this proximity, the comet is subjected to extreme solar heating, with temperatures reaching tens of thousands of degrees Celsius in the vicinity of the Sun. The intense energy from the Sun causes the comet's icy nucleus to sublimate rapidly, releasing gas and dust in a process known as outgassing. This outgassing forms the characteristic coma, a glowing cloud of gas and dust, and the ion and dust tails that extend away from the Sun. However, the close approach to the Sun also exposes C-2025 R2 SWAN to powerful tidal forces. The Sun's gravitational pull is strongest at perihelion, and if the comet's nucleus is structurally weak, it may fracture or even disintegrate entirely. This phenomenon, known as cometary disruption, is a common fate for comets that venture too close to the Sun. Historical examples, such as Comet Ison 2013, illustrate the dramatic consequences of a comet's perihelion. Ison reached a perihelion of 0.015 AU, just over 2 million kilometers from the Sun, and was ultimately torn apart by solar tides, leaving behind only a faint trail of debris. The survival of C-2025 R2 SWAN depends on several factors, including the size and composition of its nucleus, the rate of sublimation, and the structural integrity of its icy body. AMPA's larger nucleus, with a more robust internal structure, may withstand the Sun's forces longer, while a smaller or loosely consolidated nucleus is more likely to fragment. Additionally, the comet's rotation rate plays a role in its stability. Rapid spinning can cause uneven heating and mechanical stress, increasing the likelihood of disintegration. As C-2025 R2 SWAN approaches its perihelion, astronomers will closely monitor its behavior to determine whether it endures the Sun's onslaught or succumbs to the inevitable forces at play. In contrast to C-2025 R2 SWAN, 3I Atlas is following a significantly safer trajectory with a perihelion distance of 1.36 AU, placing it between the orbits of Earth and Mars. This distance, approximately 23 million kilometers, 26 million miles from the Sun, allows the comet to avoid the extreme conditions that threaten C-2025 R2 SWAN. At 1.36 AU, the solar heating is still substantial, but it is not strong enough to cause rapid sublimation or catastrophic structural failure. This enables 3I Atlas to maintain its structural integrity as it continues its journey through the inner solar system. Moreover, 3I Atlas is on a hyperbolic trajectory, meaning it is not gravitationally bound to the Sun and will eventually escape the solar system. This trajectory is a defining feature of interstellar comets, which originate from outside our star system and are influenced by the gravitational interactions of distant stars and molecular clouds in the Milky Way. Unlike C-2025 R2 SWAN, which is likely a native comet from the outer solar system, 3I Atlas is a rare visitor from interstellar space, making it an invaluable subject for scientific study. The perihelion distance of 3I Atlas also influences its visibility from Earth. While it is not expected to become a bright naked eye object, it will be observable through telescopes and space-based instruments such as the Hubble Space Telescope and the James Webb Space Telescope. These observations provide crucial data on the comet's composition, structure, and behavior, offering insights into the nature of interstellar comets and the environments from which they originate. For example, spectroscopic analyses have revealed that 3I Atlas is rich in carbon dioxide and contains traces of water ice, carbon monoxide, and other volatile compounds, suggesting it formed in a cold, distant region of its home star system. The disparity in perihelion distances between C-2025 R2 SWAN and 3I Atlas underscores the critical role that this parameter plays in a comet's survival. AMPA's closer perihelion exposes a comet to more intense solar radiation, which can accelerate sublimation and trigger structural failure. Conversely, a more distant perihelion allows a comet to maintain its integrity and continue its journey without succumbing to the Sun's destructive forces. This distinction is particularly relevant for C-2025 R2 SWAN, which is at a much greater risk of disintegration due to its proximity to the Sun. In addition to survival, perihelion distance affects a comet's visibility and the types of observations that can be made. Comets that reach perihelion at closer distances tend to brighten more rapidly, sometimes becoming visible to the naked eye, but they may also fade quickly if they disintegrate. In contrast, comets with more distant perihelia may remain visible for longer periods, allowing for extended observations and a more detailed understanding of their properties. C2025 R2 SWAN's close approach may result in a brief but intense display, while 3i Atlas offers a slower, more sustained opportunity for study. Ultimately, the perihelion distance is a key determinant of a comet's fate. Whether a comet survives its encounter with the Sun or is torn apart by solar forces depends largely on how close it ventures to our star. The contrasting trajectories of C2025 R2 SWAN and 3i Atlas highlight the diverse outcomes that comets can experience and the importance of understanding the factors that govern their behavior. In the next section, we will explore the broader implications of these comets' perihelion distances and what they reveal about the nature of comets and their interactions with the Sun. Understanding the fate of C2025 R2 SWAN and 3i Atlas requires a deeper look into the processes that govern cometary disintegration and the unique characteristics of interstellar comets. While both comets are influenced by the Sun's gravitational pull and radiation, their distinct perihelion distances and origins lead to vastly different outcomes. C2025 R2 SWAN, with its perilously close 0.5 AU perihelion, is at a heightened risk of disintegration due to the extreme solar heating and tidal forces it will encounter. Meanwhile, 3i Atlas, as an interstellar comet, presents a fascinating opportunity to study the composition and origins of objects from beyond our solar system. Cometary disintegration is a complex process driven by several key factors, including solar heating, structural integrity, and rotational forces. As a comet approaches perihelion, it experiences a dramatic increase in solar radiation, which causes rapid sublimation of its icy components. This process, known as outgassing, leads to the release of volatile materials such as water ice, carbon dioxide, and methane, forming the comet's coma and tails. However, if the sublimation occurs too quickly or unevenly, it can create internal stresses that weaken the comet's structure, increasing the likelihood of fragmentation. One of the primary indicators of a potential disintegration event is the rate of brightening. Comets typically brighten as they approach the Sun due to increased outgassing, but an abrupt or excessive increase in brightness can signal instability. C2025 R2 SWAN exhibited signs of instability in its early observations, with a sudden brightening in early April 2025 that raised concerns among astronomers. This outburst was followed by a gradual fading, suggesting that the comet may have already begun to disintegrate. By the end of April, the comet had largely vanished from view, leaving behind only a faint dust cloud. This pattern is consistent with previous cases of cometary disruption, such as Comet C2013 A1 Siding Spring, which disintegrated after a close approach to the Sun. Another factor contributing to cometary disintegration is tidal stress. As a comet nears the Sun, the gravitational pull it experiences is not uniform across its entire structure. The side of the comet facing the Sun experiences stronger gravitational forces than the side facing away, creating a tidal force that can stretch and tear the comet apart. This effect becomes increasingly pronounced at closer perihelion distances. For C2025 R2 SWAN, its 0.5 AU perihelion places it within the range where tidal forces are strong enough to cause structural failure, especially if the comet is relatively small or loosely consolidated. In addition to external forces, a comet's rotational speed can also influence its survival. Many comets spin as they travel through space, and if the rotation is too fast, it can generate centrifugal forces that overcome the comet's internal cohesion. This can lead to the ejection of material, or even complete fragmentation. Observations of C2025 R2 SWAN suggest that it may have experienced a rotational acceleration during its approach to the Sun, potentially exacerbating its structural weaknesses. Despite these challenges, not all comets that approach the Sun at close distances disintegrate. Some, like Comet 67P Churyumov-Gerasimenko, have survived multiple close approaches due to their larger, more stable nuclei. However, C2025 R2 SWAN appears to be on a different trajectory, with its perihelion distance and observed behavior pointing toward a probable disintegration event. While C2025 R2 SWAN represents a typical solar system comet on a risky path toward the Sun, 3I Atlas stands out as an interstellar object with a completely different origin story. Unlike comets that form within the solar system, 3I Atlas hails from beyond our star system, likely originating from the distant reaches of the Milky Way. Its hyperbolic trajectory, with a high orbital eccentricity of 6.141, confirms that it is not gravitationally bound to the Sun and will eventually escape the solar system. The discovery of 3I Atlas provides valuable insights into the nature of interstellar objects and the conditions in which they form. Spectroscopic analysis conducted by the Hubble Space Telescope and the James Webb Space Telescope have revealed that 3I Atlas is unusually rich in carbon dioxide and contains trace amounts of water ice, carbon monoxide, and carbonyl sulfide. This composition differs from many solar system comets, which tend to be richer in water ice and other volatile compounds. The presence of carbon dioxide suggests that 3I Atlas may have formed in a colder, more distant environment, possibly in a star system with a different chemical makeup than our own. Furthermore, the age of 3I Atlas adds another layer of intrigue. Based on its trajectory and velocity, scientists estimate that it may be between 3 and 14 billion years old, making it potentially older than the solar system itself. If this estimation proves accurate, 3I Atlas could be one of the oldest comets ever observed, carrying information from a time when the Milky Way was still in the process of forming. This raises important questions about the evolution of star systems and the distribution of volatile materials in the galaxy. In addition to its scientific value, 3I Atlas also serves as a reminder of the vastness of the cosmos and the dynamic nature of interstellar space. Unlike C-2025 R2 SWAN, which is on a relatively short-lived trajectory within the solar system, 3I Atlas is a transient visitor, destined to leave our neighborhood and continue its journey through the galaxy. Its hyperbolic path ensures that it will not return, making it a rare and precious object for scientific study. As we continue to observe 3I Atlas, we gain a unique window into the conditions of other star systems and the mechanisms that govern the formation and evolution of comets. The fact that it remains intact despite its close approach to the Sun, even at a perihelion of 1.36 AU, suggests that it possesses a robust internal structure capable of withstanding solar heating. This resilience, combined with its interstellar origin, makes 3I Atlas an extraordinary object that deepens our understanding of the universe beyond our own solar system. The perihelion distances of C-2025 R2 SWAN and 3I Atlas are not merely numerical distinctions. They carry profound implications for planetary defense, scientific research, and our understanding of the cosmos. These distances determine not only the survival prospects of the comets, but also their potential impact on Earth and the broader solar system. By examining the consequences of these perihelion distances, we can appreciate the intricate relationship between cometary dynamics and the safety of our planet, as well as the scientific opportunities they present. The perilous 0.5 AU perihelion of C-2025 R2 SWAN places it in a high-risk category for disintegration. While this may seem like a natural endpoint for many comets, the process of fragmentation and disintegration is not without consequences. When a comet disintegrates near the Sun, it releases a significant amount of debris, including dust, ice particles, and potentially hazardous fragments. Although the likelihood of these fragments posing a direct threat to Earth is low, the possibility cannot be entirely dismissed. Smaller particles from a disintegrated comet could contribute to meteor showers if their orbits intersect with Earth's, while larger fragments might require monitoring for potential impacts. In the case of C-2025 R2 SWAN, astronomers are closely tracking its trajectory and behavior to assess the risk of debris reaching Earth. The comet's closest approach to Earth is projected to occur in October 2025 at a distance of 0.26 AU, approximately 39 million kilometers. While this distance is far enough to mitigate immediate danger, the unpredictability of cometary disintegration events necessitates vigilance. The lessons learned from past cometary disruptions, such as the 1994 impact of comet Shoemaker-Levy 9 on Jupiter, underscore the importance of understanding the behavior of comets as they approach the Sun. Such events serve as reminders of the potential hazards posed by celestial objects and the need for robust planetary defense strategies. In contrast, 3I Atlas's perihelion distance of 1.36 AU ensures a safer passage through the inner solar system. Its hyperbolic trajectory and lack of gravitational binding to the Sun mean it will not return to the solar system, eliminating the possibility of repeated close encounters with Earth. Furthermore, the comet's path brings it to within 0.19 AU of Mars in October 2025, but it will not come closer than 1.80 AU to Earth. This safe distance minimizes the risk of any direct threat to our planet. However, the study of 3I Atlas offers an opportunity to refine our understanding of the trajectories and behaviors of interstellar objects, which could inform future planetary defense efforts. Beyond planetary defense, the perihelion distances of C2025 R2 SWAN and 3I Atlas provide valuable scientific insights. For C2025 R2 SWAN, its close approach to the Sun offers a unique opportunity to study the effects of extreme solar heating on cometary nuclei. Observing the disintegration process in real time allows scientists to analyze the composition of the comet's dust and gas, as well as the mechanisms driving its fragmentation. These observations contribute to our understanding of the physical and chemical properties of comets, shedding light on their formation and evolution in the outer solar system. The study of 3I Atlas, on the other hand, opens a window into the chemistry and origins of interstellar comets. As the third confirmed interstellar object to visit our solar system, 3I Atlas carries with it the signatures of its distant home. Spectroscopic analyses have revealed a composition rich in carbon dioxide and other volatile compounds, which differ from the typical makeup of solar system comets. This divergence suggests that 3I Atlas may have formed in a star system with a different chemical environment, offering clues about the diversity of planetary systems in the Milky Way. Moreover, the age of 3I Atlas, estimated to be between 3 and 14 billion years, provides a glimpse into the early history of the galaxy. If the comet is indeed older than the solar system, it may have originated from a now-defunct star system or a region of the galaxy that predates our own. Studying such an ancient object allows scientists to piece together the evolutionary pathways of stars and planetary systems, enhancing our understanding of the universe's history. The contrasting trajectories of C2025 R2 SWAN and 3I Atlas highlight the dynamic nature of the solar system and the interconnectedness of celestial phenomena. C2025 R2 SWAN's elliptical orbit, which may eventually return to the outer solar system if it survives its perihelion, illustrates the cyclical nature of cometary motion. In contrast, 3I Atlas's hyperbolic trajectory underscores the transient and unpredictable nature of interstellar visitors. These differing paths reflect the diverse origins and destinies of comets, emphasizing the vastness of the cosmos and the intricate web of gravitational forces that govern their movements. The study of comets also bridges the gap between planetary science and astrophysics. Comets like C2025 R2 SWAN and 3I Atlas serve as natural laboratories for investigating the effects of solar radiation, tidal forces, and interstellar environments on celestial bodies. They offer insights into the processes that shape the solar system and the broader galaxy, as well as the potential for life-sustaining materials to be transported across vast distances. For example, the organic compounds found in comets have been hypothesized to play a role in the emergence of life on Earth, and the study of 3I Atlas could shed light on the prevalence of such materials in other star systems. The perihelion distances of C2025 R2 SWAN and 3I Atlas exemplify the dual roles that comets play in the cosmos. C2025 R2 SWAN serves as a reminder of the delicate balance between survival and destruction, illustrating the challenges faced by comets as they navigate the Sun's gravitational pull. At the same time, 3I Atlas offers a glimpse into the mysteries of interstellar space, providing valuable data on the composition and origins of objects from beyond our solar system. Together, these comets enrich our understanding of the universe, highlighting the importance of continued research and observation. As we continue to track their journeys, we are reminded of the vast interconnected web of celestial phenomena that shape our existence and the endless possibilities that await exploration. As we draw to a close, the stories of C2025 R2 SWAN and 3I Atlas remind us of the vast, intricate dance of celestial bodies that govern the universe. These comets, each on a unique trajectory, embody the delicate balance between destruction and discovery, survival and transformation. One races toward a perilous encounter with the sun, teetering on the edge of disintegration, while the other glides through the inner solar system, a silent traveler from the depths of interstellar space. Their fates, shaped by the invisible forces of gravity and solar radiation, offer a glimpse into the grand scale of cosmic processes that have played out for billions of years. Yet, beyond their individual journeys, these comets serve as profound reminders of our own place in the universe. They challenge us to consider how fleeting our own existence seems in the grand tapestry of time and space. Just as C2025 R2 SWAN may vanish in a burst of light and dust, so too do we, as individuals, exist within the vast continuum of cosmic history. And yet, like 3I Atlas, we are also explorers, seeking to understand the unknown, driven by the same curiosity that compels us to gaze at the night sky and wonder. The study of comets is more than an exercise in astronomy. It is an invitation to ponder the origins of the universe and our role within it. Every fragment of a disintegrated comet, every spectral signature of an interstellar visitor carries with it the echoes of distant worlds and ancient histories. Through these celestial messengers, we are reminded that we are not isolated in the cosmos. We are part of a larger story, one that stretches across galaxies and epochs, written in the language of light and matter. As we continue to observe C2025 R2 SWAN and 3I Atlas, we are not merely witnessing the fate of two comets. We are participating in a timeless dialogue between humanity and the universe. Each observation, each discovery, deepens our understanding of the cosmos and reinforces the idea that we are inextricably a part of it. The universe is not a distant, indifferent void, but a living, breathing entity, constantly unfolding in ways we are only beginning to comprehend.